Welcome to this episode of Real Chemistry. Today we're going to be talking about how energy is converted into mass in nuclear weapons. In particular, we're going to take a look at the Castle-Bravo test, which is the largest nuclear weapon ever set off by the United States. So here you can see the mushroom cloud coming from Castle-Bravo. So this is a large explosion. The yield of this is 15 megatons. That means 15 million tons of TNT. So that's a lot of TNT. That's how much TNT you'd have to explode if you wanted to get the same size mushroom cloud. Now, the question is, where did all this energy come from? And as with all nuclear explosions, it came from destroyed mass. So mass is actually destroyed and converted directly to energy. The thing about this process is even just a little bit of mass destroyed releases huge amounts of energy. So for example, in this process, the mass destroyed was just 0.7 kilograms, or a little over a pound. A little over a pound, that's it. So take like 2 soda cans. That's about the mass that was destroyed. And so you can see how much tremendous amounts of energy can be released by destroying just a little bit of mass. And what we're going to do now is just take a look at what that looks like mathematically. So this says what energy is released by the Castle-Bravo bomb if the mass destroyed is 0.7 kilograms. And what we're going to use is our famous equation, E equals mc squared. And we're doing this in kind of the easy way. There's a really complicated way where you can look at the actual nuclear chain reactions and calculate the difference in mass before and after. And those difference in masses are like minuscule. So mathematically, it gets pretty challenging just to like keep track of all the digits. Here, we're just taking the total mass destroyed, which makes this problem a little easier, but still communicates to you where that energy ultimately comes from. This C here stands for the speed of light. The speed of light is huge, 300 million meters per second. And then you'll notice it's squared. And so basically, if I take a mass and then I'm going to multiply it by this number twice, you can see why that energy gets so large. So energy then is equal to mass, which I know is 0.7 kilograms. Whenever I plug mass into here, it has to be in kilograms. And then I'm going to multiply that by speed of light squared. When I do that, I'm going to get 6.3 times 10 to the 16th joules. So joules is a standard measurement of energy. This 10 to the 16th part means that there's 16 zeros in that energy. So if I write that out in standard notation, then I'm going to write my 3, and now I have to add 15 more zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 joules. So you can see that we've released a crud load of energy just from destroying a very small quantity of mass. The reason it gets so big during this conversion process, at least mathematically, is because you multiply by the speed of light squared. So you're multiplying by a really big number twice, and that means even when you destroy really small bits of mass, you destroy or you release a very large amount of energy. Thanks for watching this episode of Real Chemistry.